So the subject that about which we have to talk is basically the welding, or broadly, you see, this subject falls, or this topic falls under the joining. Okay, because in joining you have number of other things, and not necessarily welding only. So the joining is a much bigger umbrella related with the fabrication techniques. So when joining is used, basically we'll use the word joining because we have a lot of joining processes, not just welding on all the topic, the title subject, chapter title is welding. What is the need of using this the welding or the joining based manufacturing processes? You know, there are the four most conventional manufacturing processes. You know, what is the purpose of manufacturing processes is to realize the desired size and shape of components. This is one major objective, shape of components, and which is done through the, like say, the processes using the casting or machining, then your forming and welding, or you can say joining. These are four the most common approaches or the processes used in manufacturing to make the components of desired size and shape. Apart from these four, we have another category of the processes where you can say we are interested in improving the performance or properties of the components which have been made using these processes. Okay, so whatever we are getting, if we are not satisfied or not suitable for a given purpose, then we would like to improve the properties and performance of the components made by either casting, machining, forming or welding. So there are two broad processes under this category. One is called, like say, the case or surface hardening. Case or surface hardening. Okay. So in this case, only the surface properties are altered. Like this is the bulk component, only the surface layer properties are modified in case of the this surface hardening or case hardening. But there is another, sometimes we don't need just the surface property improvement, but we also need the bulk properties improvement, bulk material property improvement. Bulk properties of the entire material is to be improved. So in that case, we don't need just the surface property enhancement, but entire section needs to be improved, say in terms of tensile strength, or in terms of ductility or toughness or corrosion resistance, or anything else that is of importance for the functionality of a given component. Okay, so in this category we have the heat treatment. I hope you would have studied some of these processes, but that is not our interest to talk about these processes. See, this is what the entire group of the conventional manufacturing processes include. Okay, we have to get the desired size and shape of the components using these four conventional processes, and the performance improvement or property improvement using case hardening or surface hardening, or the bulk material property enhancement. So these are also termed as like surface engineering, where only we are interested in engineering the surface characteristics. Okay, surface engineering. Okay, and here we have the heat treatment for bulk material property improvement, and in this category we have processes like annealing, normalizing, quenching, then there is a tempering, then os tempering, mar tempering. There are number of the heat treatment processes which are used for improving the bulk material properties. These are mostly used for the steels, no, and these are not the metals in form of only, we don't use just the steels in engineering industry or in our you can say industry or society, but we have to use number of other materials which may be in form of, like say, the titanium, aluminum, copper, magnesium. These are completely different from the ferrous metals like steel, cast iron, etc. So they needed the different kind of the heat treatments for property improvement. These are, like say, in form of T6 heat treatment, T4 heat treatment, or annealing. So these are the different heat treatments which are used for bulk material property enhancement. Okay, now coming back to our joining. Okay, so when we use probably in this course you are studying, you would have studied, I believe you would have studied some other processes in some other subject. In this subject you are studying casting and maybe forming also, apart from the building. Okay, so their approaches are different, each one works on the different approach. So let's talk about the welding or the joining and its need. What purpose is solved by the this group of the processes. Okay, this is the first thing. This is known as a fabrication technique. The welding or joining are known as fabrication techniques. And what are the uses and why at all this is needed? You see, there are few compelling situations where we want, okay, let us use joining or welding. Like casting, you can use for simple shape to the fairly complex, but not extremely complex. Sometimes you find like you are not in position to prepare the mold of the desired complex geometry. So you have to make the two simple components using the casting or forming or machining, and then let us bring them together. And to bring them together to get the desired complex shape geometry, we need to use the joining or the welding kind of thing. So the one main objective of using welding or joining is to realize the desired complex shape geometries which are not otherwise doable using the conventional other processes like casting, machining or forming. We realize the comparatively or little simpler shapes, and then those simpler shapes are brought together by the joining or the welding one. So this is one major purpose of using joining, to realize the desired complex shape and geometries. Okay, the second another objective is like you can make the components of, like say, 200 gram or 5 gram or 2 kg or 10 kg or 2 quintal, but if it is in hundreds of the tons, then you cannot use any single process to make the products, to make the systems. So like say to develop very large size, to develop the another major objective is to develop very large size systems. Like say you must have seen, you have to Howrah Bridge, or like say the bridge on Ganga in Allahabad, or very old bridge in like say even in Delhi. So the very large structures like the steel bridges is one typical example where, like say, you use simple girders, rods, plates, and then they are put together to have a system which is which can serve the purpose actually. So this is one most common example. The second one, you see, to make the simpler shapes, like you need to make the ships. No, ships are, no, they are very large in structure, maybe hundreds of the tons in the weight you have to use. They will be running maybe say half a kilometer or 1 kilometer depending upon the size. So you cannot use even a single process. You have to bring the large number of the components together in order to get the desired size and shape. And the same is true for building the normal conventional systems. Like even if you take a simple pen, you need to assemble small 2-3 components. Like there can be a car which uses like say at least 10 to 15 types of the material of the different obviously the dimensions and the geometries. And see, joining not just the one type of metal with the similar type of the metal of other component, but sometimes you need like aluminum is to be joined with the steel, or aluminum is to be joined with the glass. So there is no match between the characteristics of the two. Still the joint is to be developed. If you talk of like a lot of the nowadays the car which are being developed, they are made of like say aluminum is being joined with the steel, or aluminum is joined with the magnesium, or even with the plastics. In a typical car, we have 5,000 to 6,000 number of the joints, and although spot weld joint is one of the most common, but apart from that there are a lot of newer joints which are also being developed in order to develop the multi-material joints. No, when the different types of the materials are to be put together, they lead to the lot of difficulties in joining. Like the two persons having a similar characteristics can be good friends, but the two persons having completely different characteristics, you may find it difficult to have at least a friendship. Okay, so the compatibility between the different metals again bring in the another set of the problems for joining. But if you have to make something which really works, which is good for the society, which is needed, then of course you need to find out the solutions. And that is why you need not just to join the similar type of the metal. Sometimes you need to join the not just dissimilar metals like aluminum and steel, or steel with the titanium, or aluminum with the copper, but you have to also join like the different materials. Aluminum is to be joined with the plastics, where there is one is metallic, another is non-metallic. So of course they will have a lot of difference in terms of strength, physical properties, mechanical properties, chemical properties, and they may not have any commonality to develop a joint. So the approach is going to be completely different. Okay, so this is the, like say, these are the two main purposes of using joining: to develop the large complex shape structures, or to come out with the complex geometries. Okay, sometimes you need to, like, joining is needed just for the good reliability. Like aluminum copper joint can be simply developed using, like say, you just twist them, but reliability may not be good. The joint may get opened after some time. So if you have to join the two dissimilar metals, wires of say copper and aluminum, which are not really compatible with each other, so you have to use something which will bring them together, and at the same time their sustainability of the joint, the life of and reliability of the joint will also be for long. It will be good for the, otherwise you'll see you are going, your car is going, and somewhere in the middle of the road in the night you find that no joint has broken, so everything has gone out of the order and you are on the road. So the reliability is really another important thing, and certainly these different things need to be brought in together. So it is very important, like you come out with the very reliable and more acceptable and the economical joining method to bring these dissimilar kind of things also, which are really need of nowadays, because people are bringing so many things together in order to reduce the cost, in order to improve the performance, just like composite materials. Okay, so that was about like need, why at all we have to go for. Okay, so in these joining processes, what we use basically, invariably the application or use of heat is one and pressure is another. So both will be playing different role. Heat and pressure, these can be used either in singly, just use heat or forget about the pressure, or use pressure only, forget about heat, or we can use the combination of both. So you can say singly or in combination. Now depending upon the process, if you are just fusing and allowing it to solidify to develop the joint, then it's just use of heat, or you just twisting the two wires together using the pressure to and deforming them to such an extent that they really come very close to each other, using that plastic deformation, then you see there is just use of pressure, there is no use of heat in that case. And sometimes we have to use both heat and pressure. So this is one aspect. The second aspect is, so most of the joints will be needing either heat or pressure or both. Okay, so heat will be used for number of purposes, I'll come on that little later, and likewise pressure also used for not just deformation but for one number of other purposes. The second thing is in joining is about what you are joining. So joining the similar metals, okay, like say the mild steel is joined with the mild steel, or your austenitic stainless steel is being joined with the austenitic stainless steel. This is similar metal joining. Okay, they are like by and large the composition properties, physical, chemical, mechanical properties are same. Okay, so you see that what happens when the two components of similar type are subjected to either pressure or heat. Okay, so you are applying heat or you are applying pressure to these. So because of the similarity of both the members in terms of physical, mechanical, chemical properties, due to the similarity of these properties, now they will respond in the same way. Like its expansion will be similar to the one expansion of one part will be similar to the other part. Mechanical properties, their weakening will be same in both the components, or strengthening will be same in both the components, fusion will be same in both the components, deformation will be same in both the components. So it is easier basically when the response of the both the parts made of the same metal, because of the similarity in physical, mechanical and chemical properties, they respond basically in the same way to both heat and pressure, and that is why you find the similar metal joining little easier. No, similar metal joining is easier, but it is not so in case of the dissimilar metal joining. Why? Because one metal is like say one is completely different from the another one. Like say the metal B and metal A, this has got melting point of 1600, this has got 400. Okay, this has got a strength of say 800 MPa, right, and this has got a strength of 150 MPa. And physical thermal conductivity also, say this thermal conductivity of this one is just 8 units, and here it has got 20 units. So the completely different kind of the metals. The thermal conductivity, thermal expansion coefficient, here say it is just 12 units, and here it is say 22 units. So these are the typical characteristics of like say non-ferrous metals, and this is ferrous metals. The point is, two metals will completely, they because of the difference in melting point, yield strength, thermal expansion coefficient, thermal conductivity, they will behave completely different way when the heat or pressure is applied. So you cannot expect like they will expand and the contract by the same magnitude, they will fuse by the same magnitude. You may find, okay, one has started melted, one has just one, you see B is still getting heated, and the second A is started fusing here and there, and molten metal is started flowing. Okay, so you cannot control the things. The point is, when you have completely different set of properties, the two metals do not behave and respond in the same way, and that is why you find it very difficult to join the dissimilar metals. So joining of the dissimilar metal joining is really difficult. Okay, and this is the reason. So okay, why should we talk of the like difficulties? Let us understand first what is easier to and how it is done. What are the different principles, underlying principles related with. Okay, so let's go further a little bit. In this lecture, basically, I will be talking about the fundamentals related to the joining only. Let's see how much I'm able to cover. Once we understand the fundamentals, probably it will be easier to take up the processes and other things. Okay, so what are the different approaches we have for developing any kind of the joint? Okay, the joints are actually developed. I'll give the example and the approaches which are used. One is the joint where the metallurgical continuity is realized. Metallurgical continuity is realized. So this happens when you fuse the two components together, and after the solidification you get the metallurgical continuity from one side to another. That's one case, like the two components and you are just fusing them like this, and after solidification you are getting the joint. The second case, where you have the two components, they are perfectly polished, cleaned and brought under pressure in contact with each other, and across the interface diffusion takes place. So in that case also you will be having the metallurgical continuity. Okay, so that's the diffusion phenomena that will be working on to develop the metallurgical continuity between the two components. Okay, this is one. The second is your mechanical interlocking. So in this case, there may be metallurgical continuity, but interlocking also plays a bigger role. What is the mechanical interlocking? It's just like you have the two components and you just drill a throw hole and just put in the nuts and bolts here and there like this. This is one way. This is simplest way. You put rivets or nuts and bolts kind of thing. The second way is take the two components, okay, and apply the controlled interfacial deformation. So one metal mixes with the another metal in solid state like this. So the metal A will be getting mixed in the solid state itself with the another metal and leading to the mechanical interlocking at the interface. So this is what happens in case of the ultrasonic welding, electromagnetic welding, explosive welding, even your little deformation and interlocking takes place in case of the diffusion welding also. So but these are the three very common the processes where mechanical interlocking is involved. Third one is where, like say, the physical and chemical interactions take place at the interface. So this is where we have the, like say, you take the two components and between the two components you put something, like say you put the brazing material in brazing or soldering processes, right, or you put in some kind of the adhesive material like epoxies, resins, hardeners, fevicol, M-seal. These are there few trade names or few like the chemical names. So you put the adhesive, and adhesive will be interacting chemically, physically with the two components, and joint is developed. In this case, both the components to be joined remains in the solid state. There is no fusion as such. Both remains in solid state. So the fusion, what we have seen only in case of the fusion welding. In the diffusion also, like we were just two components were being polished, smoothened, and then brought in contact with each other under pressure, and the diffusion was facilitating the development of joint. Interestingly, You see, the metallurgical joints may be extremely good in terms of the joint performance. What is the joint performance? Before going into that, let me talk a little bit about. Take the two components like this, same metal, okay. So both are having say strength, same, they are same metal, so strength say 200 MPa both the sides. Okay, when you develop the joint, let's say joint is developed at the interface, and you perform the test, tensile test. So obviously you will be getting, say, engineering stress strain diagram like this. So whatever is the your the fracture stress or ultimate UTS, ultimate strength, see, that you can compare with the base metal's own strength. Say base metal strength is 200, and after testing, if you find the joint is intact, there is no failure from the region close to the joint, but the failure is occurring from the nearby regions. Okay, so obviously we will say that our joint is stronger than the base metal. Okay, so the means joint is stronger than the 200 MPa, isn't it? So in that case, if the joint is stronger than the base metal and failure is occurring from the base metal at far away location from the weld joint, then you see the joint efficiency we can safely assume is greater than 100%. But if that is not the case, if we get the joint strength of, like say, 180 MPa, the failure occurs from the interface, from the weld itself. If the failure is occurring from the weld, then what we'll say, the strength of the joint, that is 180 MPa divided by the strength of the parent metal or the base metal, that is 200 MPa. Okay, so what we will be getting basically 18 by 20. So this is what you will be getting. So it is your 90% strength. So that's what you will be getting, 0.9 and multiplied by 100. So your joint strength is 90%. So the point here is metallurgical continuity realized through the diffusion bonding usually gives us the strength which is greater than the base metal strength. So joint efficiency is greater than 100%. Our belts are most of the time stronger. But there are a number of cases where if there are defects, if there are discontinuities, if there are weak porosity or defects, then certainly the weld will be weaker and the joint efficiency may be 50%, 60% also. So 50% strength efficiency, joint efficiency means your weld will take just 100 MPa load stress, and for a base metal of 200 MPa strength, so your joint efficiency will be 50%, and the regions you have to explore. So the now interesting thing here is what, like say, if there is a weld, right, like this, so the location of the failure will indicate what is the weak point in this joint. There are three locations. One is, say, A, base metal, another base metal, and B is the weld. And what we have seen, when there is application of heat or there is application of pressure, the properties of the base metal both sides in vicinity of the weld are affected basically like this. So this zone, which is not actually melted but it is heated, and so this zone also experiences changes in terms of the properties, like say your mechanical properties or metallurgical properties, both are basically affected due to the heat which has been applied, due to the pressure which has been applied. So what we say, this zone which has experienced the heat of the fusion, we call it as a heat affected zone. So the zone of the base metal which is near the weld metal or weld joint, being affected by the heat will be termed as the heat affected zone. Okay, and this zone is usually it is very small. It may be, let's say, in typical steel weld joints maybe 5 mm, like both the sides. In aluminium it may be 10 mm because that is of the higher thermal conductivity. So what I was saying, if your failure is occurring from the heat affected zone, then we need to see, like, heat affected zone needs attention for improvement in the property. If the failure is occurring from the base metal, then weld metal, then weld needs attention. So in a chain, you know, there are tens of the links. So that's what here we have A, another side we have another A, another parent metal, and somewhere you have weld. This is another. That's here you have HAZ one side, and here you have another HAZ another side. Okay. So the side which fails, like if the failure is occurring from this link, that means HAZ is weak. If the failure is occurring from this link, that means this side HAZ is weak. If the failure is occurring from this link, means weld is weak. So joint is nothing, it's just like it is helping to develop a chain so that it can transmit the load, it can develop the connection, it can allow the flow of current, like that. Okay. So this weak link where from failure is occurring will be indicating the zone which needs attention, the zone which needs which is weak. So that has to be addressed to improve the joint performance. Say base metal strength here, say again take example 200 both the sides. If your weld is of 150 MPa strength and HAZ is of just 100 MPa strength, then you need the HAZ to be improved in order to improve the joint performance. Okay, so this is the another aspect. As I said, the metallurgical continuity approach of developing the joining, this gives either the joint strength 100% or it can be lower also. If it is free from the defects, most of the time it offers the good joint strength. The second, the problem with this mechanical joining or mechanical interlocking, like you have to add the metal while developing a joint in form of nuts and bolts. In car and ship, where efforts are always there to reduce the dead weight so that payload can be improved, fuel efficiency can be improved, emissions can be reduced by reducing the dead weight. But if you are developing the joints using a method which is helping or which is increasing the dead weight, then that is not considered to be a very popular approach. So in those cases where weight is not important, certainly you can use these mechanical interlocking methods of rivets and nuts and bolts. But if that is not the case, then let us use some methods which will be developing the joint without adding the weight or without significant addition to the weight of the metal. Okay, so the mechanical joining, this is good in strength, it is reliable as well, but the problem is the weight addition. So it's also not very popular in all the situations. On the other hand, lastly you have physical and chemical interaction approach, where adhesive joints or the chemical joints are developed. So there what we see, in case of the adhesive joints, the other chemical joints, like say joints, they are very weak. So the joint efficiency may be just say 20 to 50% of the base metal. So they are not designed, actually they are not used for carrying the mechanical load significant, but they are used primarily to ensure that the components remain in position. So to maintain the relative position of the two components only, the adhesive joints are preferred to be used. But if these are of the load carrying type, where the load will be acting across the joint interface, then their performance will be poor. And another issue related with these joints is what? They degrade very easily. Say under the sunlight they will degrade, under the moisture they will degrade, or under the in the effect of the chemicals they will degrade. So the problem is you cannot use these joints at number of places. And the moment your temperature goes above 100 degrees centigrade, their thermal decomposition starts, and your joint will burn off, and joint will be opened. So adhesive joints are good for very delicate or very favorable working conditions. Okay, so that was about the capability of these the joining approaches. Now I'll give the simpler example. Like, if the two components need to be joined, it will be the best if the two can be joined without doing anything. Do nothing. But things do not happen automatically. You have to do something to develop a joint. There is just one way to develop a weak joint. Like, you must have heard, like, if you put the slip gauges together, you get a joint. But that joint is very weak, not good for carrying the load, or for performing the desired function. Slip gauges are the examples where the joint is made, but the joint is very weak. It is not strong for functional purposes. So slip gauge, weak joints. Okay, then the next easier method is, let's put some adhesive between the two components so the chemical interactions take place and the joint is developed. But these joints are very weak. The next easier method is, between the two components, let's put some kind of the low melting point material, like brazing or soldering material is put. So your metal is of say 400 degrees centigrade, and you are putting the base metal, the melting point is 800, and you are putting the low melting point metal like say 450 degrees centigrade or 250 degrees centigrade in between. So the filler only will be melting, but there is no change, there is no melting of the base metal. So this is the principle which is used in case of the brazing and soldering. But because of the low melting point, these are very weak joints, but still they develop the joint. The joint, although, is weaker than the simple metallurgical joint which is developed through the fusion or solid state joining approaches. The next approach is fusion, where you take two components and fuse them together like this. Just fuse the two edges and develop the joint after the solidification. So this is fusion. So just now I have explained, like, fusion joint are most of the time they are very good if they are free from the defects and discontinuities. And then lastly we have one more, the mechanical interlocking. Like, they take the two components like this, so one is mixed with the another like this. So this is the mechanical interlocking. Now if you see here, what is interesting, let me give some kind of the naming also here. 1, 2, 3, okay, then 4, actually mechanical interlocking 4, where there is no heat application, then 5, and then 6. So what is happening here, in the minimum heat for 1, then 2, no heat. Minimum or no heat. Let me write no heat. Okay. For 3, the little heating is needed in adhesive joining in form of curing. So little heating is used. 4 is mechanical interlocking. Because of the deformation, some minor heat is generated due to the deformation or due to the friction. So you can say less heat is there in case of the 4. Then in 5, what we have to supply the heat to the base metal and to the, so little more heat is used in case of the 5, brazing and soldering. And in 6, where fusion is there, maximum heat. So 1 to 6 we have increasing the processes with the increasing amount of the heat. increasing amount of heat which is to be supplied. And you know, like if you take the two metals like this, and the moment you supply the heat, the both metal properties are affected or they get modified. So if you supply less heat, the less change. If you supply more heat, more change. So more deterioration to the base metal properties, more heat affected zone is formed when you increase the amount of heat. So this in turn leads to the reduced joint performance. So what is important basically, it is the best if you can develop a joint with the minimum possible heat or no heat. But if that is not the alternative, like say in any case if you have to use the fusion joining, then let us fuse the things together with the minimum possible amount of the heat. Okay, so this point has to be kept in mind. Heat for fusion, amount of heat to be supplied for fusion welding is maximum, then somewhat less for brazing and soldering, further lesser for mechanical joining, then further lesser for adhesive joining, and then you can say the slip gauges, and then doing the joint without doing anything. So this is the kind of sequence. We always make the efforts to develop the joint with the minimum possible heat so that there is no deterioration or minimum deterioration to the base metal or parent metal properties. Okay. Now, so what is the purpose of applying the heat in joining? So you have seen the processes like the approaches, you can say. So the fusion is one. The heat in fusion welding is used for fusion or melting the fairing surfaces. Fusion or melting the fairing surfaces or the edges of the fairing surfaces or edges of the components, right, to be joined. This is one. Apart from the fusion, the heat is also used intentionally to realize the thermal softening of the metals to be joined, and this is used. So the first one is important for the fusion welding. The second one is important for the processes where the mechanical interlocking or the deformation is being used to develop the joint. Okay. Third purpose which is played is to facilitate the diffusion. Like I said, you put the two components together, very cleaned and smoothened under pressure, so across the interface diffusion takes place. So the heat also helps, the diffusion is a time and temperature based phenomena. If the heat supplied is enough to raise the temperature so that sufficient diffusion is realized across the interface to develop the joint, and this is typically used in the diffusion bonding, is one of the joining processes. Okay. Third one, or you can say the fourth purpose, which is realized in the fourth purpose of applying heat in joining is to facilitate the cleaning. How the cleaning is facilitated? Like say there are two components to be joined, you apply heat using suitable source. It may be flame, it may be arc, it may be radiation, it may be electrical resistance heating, it may be frictional heating, number of things. So heat applied, you see what it will be doing. So application of heat will be raising the temperature. So when there is a rise in temperature of the surfaces, whatever moisture you have, that will be evaporated. Moisture evaporation. Likewise, evaporation of all chemicals and compounds like paint, oil present at the surface. So organic compounds present at the surface, they are evaporated. Evaporation of chemicals and compounds present at the surface. That's the second. If there are oxides which are present, then oxides let's say this is this component, and here you have thick layer of oxide. The oxide will be expanding at a different rate as compared to the base metal because of difference in thermal expansion coefficient. Okay, so when you heat, the base metal expands more than the oxides, and so that's how the oxide layer is uh, gets eliminated from the surface, gets removed from the surface. So the oxides are removed. This is one. So basically embrittlement of the oxides take place sometimes. But there is another aspect also, like there are few metals which have very good affinity with the atmospheric gases, so they also leads to the oxidation. So your heat can also lead to the compromise with the cleaning as well. Okay, so these are the few this is how the cleaning happens in case of when the heat is applied for developing the joint. We are not talking about it is fusion or solid state or any particular joining approach. It is like whenever heat is applied, these things will be happening. Okay, let me give you a simple example how the thermal softening is happening and what is the role, its role, and how does it happen. So let's say you increase the temperature. This is room temperature, and say this is the increasing temperature. Just for example, say 800 degrees centigrade. Here I will write room temperature. So if you take the metals like aluminum is weaker and it will soften very rapidly like this. Just one example. And if you talk of say the steel is stronger a little, but it also softens like this, mild steel. And if you take the example of say stainless, austenitic stainless steel, it may sustain the strength little for higher temperatures. So say this is an example of ASS. The point is, say yield strength. So the point is here, few metals soften very rapidly, few will be resisting the softening little more. So this is what you can say, the yield strength is more, metal is hard, yield strength is low, metal is soft and of the low strength. So because of rise in temperature, all metals will be getting weakened or softened. This softening is good for the deformation. So in solid state joining, if the softening is happening, it will help in good interfacial deformation, interfacial mechanical interlocking, mixing, good metallic bonding. So all those things will be helpful if there is a rise in temperature of the components due to the application of the heat. Okay, so this is what is there in the the heat application. But when the pressure is applied, pressure is helps in obviously realizing the deformation, interfacial deformation, like say the two components to be joined. So the deformation just near the surface layers or bulk material deformation is realized. So based on that we say there is a macro deformation or micro deformation, which may be say 5 to 10 micrometer only, and here maybe 5 to 10 centimeters as well. So depending on the processes in friction welding, friction stir welding, or your forge welding, cold welding, all these will be needing lot of deformation. But ultrasonic welding or your electromagnetic pulse welding, electromagnetic welding, or your explosive welding, all these will be needing very limited interfacial deformation for developing the joint. So the one application of the pressure is to facilitate the deformation. The second is it also helps in little cleaning, because whatever the oxides, impurities are there, they will be squeezed out from the interface. So the cleaning or squeezing out of the impurities from the interface, that will also be helped by the application of the pressure. Okay, so these are the two things which are realized, and whenever there is a deformation, it will be helping to improve the metallic intimacy, metallic closeness, or metallurgical contact between the two is established for facilitating the diffusion across the interface. Okay, so this is about the role of. So So this is where probably I will stop today. I'll continue the about these fundamentals related to the joining tomorrow as well. Thereafter, we'll take up our the regular topics like classification or the welding processes. Okay, the two lectures I believe will be very helpful to understand the fundamentals related with these joining, whether it is solid state or fusion, it is same material.